Welcome to qnawire.
In this problem on magnetic forces and magnetic fields, we are told that 4 long parallel power lines each carry the same current of magnitude 100 amperes, and the cross-sectional diagram represents a square with a side length of 20 centimeters. We want to find the magnetic field at the center of the square for 3 different arrangements. Now, firstly, let's look at part C of the problem. So in part C, we can label the currents as in the diagram A, B, C, and D. The magnetic field due to C and B are additive, as well as the magnetic fields due to A and D. And so this tells us that the resultant magnetic field is to the left, and the angles are both 45 degrees. So we can then find this resultant magnetic field at the center of the square, B, and B is BA cos 45 degrees plus BB cos 45 degrees plus magnetic field due to C, BC times cos 45 degrees plus BD cos 45 degrees. But these magnetic field strengths are all the same since the currents are the same. So we can write this as 4 times BA times the cosine of 45 degrees. And we can write this as 4, and we can expand the magnetic field, since this is a long straight current carrying conductor, as mu naught I over 2 pi r. And this is multiplied by the cosine of 45 degrees. Now r with some Pythagoras is equal to the square root of 10 centimeters squared, or 10 centimeters all squared, plus again 10 centimeters all squared, which gives us the distance at the center of the square to be 0.1 times the square root of 2 in meters. So we can put this value into the expression for the magnetic field, and we can find the magnetic field B to be 4 times mu naught, which is 4 pi times 10 to the minus 7, and that's Tesla meter per ampere, that's SI units, multiplied by the current I, which is 100 amperes, divided by 2 pi times distance to the center of the square, 0.1 times the square root of 2 meters, and all this multiplied by the cosine of 45 degrees. So hence we get the resultant magnetic field to be 4 times 10 to the minus 4 Teslas, and this magnetic field, as we showed in the diagram, is to the left. So that's the magnetic field in part C, our third arrangement of the currents. Now for part A and B, the magnetic fields due to the currents at opposite corners of the square cancel, and so the magnetic field at the center of the square in both cases are 0.